figure is Nikita. And we'll talk about bispectrality of Ruijsenaars hyperbolic model.
Okay, thank you. So first of all, I wanted to thank the organizers for the conference and participants for the interesting talks. So my talk will be devoted to this particular quantum integrable model, which was discovered by Simon Ruijsenaars quite long ago. And moreover, I will focus on one particular property of this model, which is named bispectrality. So the talk, I wish to explain what it is and how it is realized in this particular model and why it is interesting to look at it. So everything I will say will be based on our recent work with Sergei Dekachov, Sergei Kharchov, and Sergei Kharoshin. So first of all, what is bispectral problem in general? This is a situation when some eigenfunction of the quantum model satisfies solves two spectral problems simultaneously. So usually in quantum mechanics, we have only the first line of the system. So we want to diagonalize some operator, which often is the Hamiltonian of the system. And this operator acts in some representation. So here it acts on the coordinates x, and its eigenvalue is labeled just by lambda. And of course, it can be any function of lambda. This is just simple parameterization. And remarkably enough, there exist situations when the same function as a function of lambda, its eigenfunction, solves some other spectral problem with some different operator h hat, which is already an operator acting on the lambda variables, and whose eigenvalue in turn depends on the coordinates x. So again, it can be any function of coordinates depending on the problem. So the simplest example is shown here when the eigenfunction is just this plane wave, and both operators are derivatives with respect to the x and lambda variables. So this is probably too simple, and a more involved but probably also familiar example is the example of classical orthogonal polynomials. So if you take, for example, the Hermite polynomials, then from high school, you may remember that the Hermite polynomials satisfy some differential equation, and this will be the first line, and some recurrence relation. So there's a recurrence relation, and in the case of Hermite polynomials, this variable lambda is a discrete variable which labels the order of this polynomial. So this setting was observed in a lot of cases, and these are just one-dimensional cases, but it actually was observed for the last 20 years or so in a lot of multidimensional integrable models. So usually, of course, you have again only the first line, and it's a challenge to find some explicit form of the second equation, to find some explicit form of this h hat operator, and then it can be used to study this problem. So now I wish to explain how this situation is realized in the Ruijsenaars model.
I'm a bit confused because in certain sense, if this h and h hat are different operators, yes, this h hat exists almost always, yeah, but it can be just variably.
Yes, yes, of course. In practice, we of course it's just a position operator written in the spectral variables.
Well, like in the integrable case, you have two type of double variables,
yes,
momenta and action and yeah. And if you relate this second operator to this action and variables, yeah, it always exists. But in most of the cases, it's just something unknowable.
Yeah.
And the point is that Ruijsenaars model is distinguished by the fact that they are identical, yeah, or at least very similar to each other.
Yes, but yes, of course, in practice, we want some nice formula for this h hat, and in Ruijsenaars, yes, as I will show, they're identical, but in some other cases, like the Toda chain or Kalodra type of models, they're not identical, but still helps.
Rational Kalodra, they also identical.
Yes, on rational Kalodra, they're identical, but in hyperbolic cases, not.
Then they change exchange with each other, but these are very special models, and there is some general recognition. But in general, if you do not specify this h hat, it's almost always true.
Yes, it's true, but as I said, it is nice to have some explicit form for this H-hat operator, and people found this explicit form and used the bispectral setting to study the properties of the model. So I will show how it can be done in this special case, but the scheme is actually universal. So first of all, I need to introduce this model and say a bit what was known for it before. So this Ruijsenaars model is a model of n particles that live on the line and whose coordinates are labeled standardly by xj. And it is characterized by the Hamiltonians h1, h2, and so on, hn. So the number of Hamiltonians is the same as the number of particles. And all of these Hamiltonians are the operators which can be written by this universal formula. So to digest this formula, let's look at two parts of it. The first part is from the right, and it depends only on the derivatives with respect to the variables x. And these operators that stand from the right are just shift operators. So they act on the functions of n variables, and they shift a particular coordinate xj by some number omega1. And the second part of the operator oppositely depends only on the coordinates, and these are these ratios of hyperbolic signs. So this operator, this part encodes the interaction between the particles. So you may notice that the interaction depends only on the differences between the particles. So only on the distance between them. And also this model includes three parameters which are marked with red color here. So the first parameter, omega1, is placed in the shift, and this is proportional to the Planck constant. The second parameter, omega1, is just the scale of interaction. It's not so essential, but it's convenient to keep it there. And the third parameter is g, is a coupling constant. So if we set, for example, g to 0, then all of these interaction terms will disappear. So that we will be left only with the momentum operators. The theory will be without interaction. So the first thing that was proved for this type of model after it was stated by Ruijsenaars is that this collection of Hamiltonians, these Hamiltonians commute with each other. One small remark is that actually Ruijsenaars didn't write precisely these Hamiltonians, but very closely related ones, but I won't write the original Hamiltonians here. So he essentially proves that these operators commute with each other, and this means that this system is, in the simplest sense, integrable. And also he proved that in the limit, in the special limit, when we rescale the coupling constant by omega1 and tend this omega1 to 0, the model which we have descends to some different model, which is called hyperbolic Sutherland model. So this limit is usually called non-relativistic because in the original physical interpretation of this model, this omega1 parameter was proportional to the coupling constant divided by the speed of light. So when the speed of light tends to infinity, we have the same, we have omega1 tends to 0. And after some work, it's not so trivial, but after some work, you can derive from the Hamiltonians I wrote previously, the Hamiltonian for this model. It looks like this, and it's probably more familiar quantum mechanical operator. So just particles on the lines that interact via some pairwise potential. So you may notice on the example of this hyperbolic collateral model that this Hamiltonian is invariant with respect to the coordinates permutations, and this is also true for the original Ruijsenaars Hamiltonians. So it's invariant with respect to this coordinates permutations. And the fact that these Hamiltonians commute raises the question of whether we can find some joint eigenfunctions of these Hamiltonians. And in particular, because this Hamiltonian is invariant, we will construct, I will explain the construction of the Bosonic eigenfunctions, the eigenfunctions that are also invariant with respect to the permutations of coordinates. So this problem of joint eigenfunctions was open for quite a long time, but it was eventually solved 10 years ago. So it was solved by Simon Ruijsenaars himself and by Martin Thalnes. And namely, they constructed some explicit formula for the eigenfunctions, which is actually, in some sense, similar to the explicit formulas that Nikita was mentioning in the case of open to the chain. So they were inspired, as they wrote, by the open to the chain case. And here the eigenfunctions depend on, of course, they depend on the coordinates, and they also depend on the spectral variables which parameterize the eigenvalues. So there are the same number of spectral variables in this vector. And there are some simple formula for the eigenvalues, which I didn't write here just because it's not so important for the talk, but it's not so complicated. The important thing of this construction is, again, as in the open to the chain previously described, this construction is recursive in the sense that the eigenfunction for the nth particle system can be obtained from the eigenfunction of the n-1 particle system using some explicit integral operator, which is denoted lambda here. So I will explain how this operator looks like in a minute, but this is the most important thing about this construction, since in the simplest case of when we have only one particle, it is just, again, as in the dotted chain, it is given by plane wave with some funny constant written here, 2 pi over omega 1 and omega 2. It's just for the simplicity of the formulas. It's not essential. And then using this one particle eigenfunction with this procedure, you can recover an explicit representation for the general case eigenfunction. So this was the major result, and let me explain how this lambda operator now looks like. So to explain how it looks like, I need to write this kernel. So as you remember, the dotted chain kernel was consisted of some simple functions. Here will be some different functions, but still the structure will be quite similar. So this operator lambda acts on the functions of coordinates. And it's recursive operator, and as it's written here, it acts on the functions of n-1 coordinate and gives you the function of n coordinate. So because in the eigenfunction here from the left, we have one additional spectral variable, lambda n. This operator also depends on the spectral variable as some additional parameter. And the dependence on the spectral variable is actually very simple. So it is marked with red here in this formula. And this kernel of this operator consists of 2 parts. The first part are these mu and k functions in the first line, which I will describe in a minute. And the second part is just simply this exponent, which contains the spectral variable rho here and some coordinates and integration variables also. So this is how it schematically looks like. Now I can explain how these mu and k functions are defined. And in order to do this, as it is written, they are defined using the function which we just call double sign function. And I need to describe what it is. So the double sign function is some special function which is a solution of these two different equations. So this is a function of complex variable z, and it depends also on 2 parameters, omega 1 and omega 2. So this has the same omegas as in the Hamiltonians. And the double sign function is some special solution of these two different equations. So in each equation, we just shift the variable z by omega 2 or omega 1 and obtain from the right the usual sign function with omega 1 or omega 2 in its argument.
One question is if the function k, the kernel function k, it's a Green function of the one operators.
What? Sorry.
Because you have the kernel function k.
Yeah.
I'm wondering, it can be considered as Green function or what kind of operator?
I don't know about this interpretation for this particular model, but we have such a construction in the case of other models.
It's not Green function because it's probably not singular when you don't say.
Yeah, but it can be made singular simply, and there is actually work by. So I don't explain how they constructed these operators, and of course everything depends on the properties or on some remarkable properties of this kernel function. And indeed, this kernel function came to this field of the Ruijsenaars and Kalodner models through the work of Edwin Langman when he considered some quantum field theory. And indeed, this kernel function came as some Green function for the anions in this quantum field theory. So, but I don't know a simple interpretation of this result. So, and it is a result about not this Ruijsenaars model, but a simpler model, which is called trigonometric Kalodner model.
And what about this analogy with some backward transformation, canonical transformation?
Yeah, I will say about it. Yeah. So it was one of the motivations for our work, and I think it was one of the motivations for their work also of Helmers and Ruijsenaars. So
I ask what will happen if omega 1 and omega 2 have rational ratio? Because in this case,
yes,
will be some additionally, could we construct it the same? I mean, because
yes, the construction doesn't depend on whether they have a rational ratio or not. So this is still will be the eigenfunction, but some analytic properties of these kernels will be different. So let me proceed. And as I said, the main building block of this kernel function, which is a double sign function, with some special solution, because you can always any solution can be multiplied by some periodic function and it will be still solution. But you may notice that these two equations are symmetric with respect to the omega 1 and omega 2 permutation. And this double sign function is also a particular symmetric solution. So this double sign function was, the name was given by the Kurokawa, and he used a lot of the theory that was developed even 100 years ago by Barnes. So now it has a lot of the properties you probably need, the integral representations, asymptotics, everything is known. And this function is also so remarkable that it was discovered quite two times more independently. Not precisely this function, but a similar close relative of it. So it was discovered by Fadeev, and he called a similar function quantum dialogograph. And it was discovered by Ruijsenaars himself in the context of his models, and he called it hyperbolic gamma function, because there is some particular limit when this double sign function reduces to the usual Euler gamma function. So it's a kind of generalization of the Euler gamma function or deformation. So you can use any of these three functions, but we use the double sign. Now, let me explain now precisely how these mu and k functions look like. And probably it's not so important to remember these formulas. The main point I wanted to make here is that these mu and k functions that depend on the vectors are just some pairwise products of the mu and k functions that depend only on the one variable, and which are kind of elementary building blocks defined here from the right. And in turn, these mu and k functions elementary building blocks are just some ratios of these double sign functions. So the main point of this page is that everything can be constructed as some products of the double sign functions. And the second important point is that, as you can see, this mu function, for example, depends on all of the parameters of the model. So it depends on the omega 1 and omega 2 parameters, and it also depends on the complete constant g. So it will be important later, and similarly for the k function. So this was the construction. Again, I won't explain it. Also, I inserted here some constant. Of course, you can multiply by any constant, and it still will be the eigenfunction. But there is some specific choice of this constant to make all its formulas simpler. I won't specify it here, but it is already there. But I will use it probably.
Does it make sense to make omega 1 and omega 2 complex?
Yeah, you can. This construction works for the complex omega 1 and omega 2 in some domain. If their real parts are positive. But Ruijsenaars didn't make them complex, we made for some reason. And everything still works. So there are actually some conditions on this omega 1, omega 2, and G, and they can be made complex inside these conditions. But I won't explain it, it's just some details. Probably we won't need them. So the mu function, actually, which I introduced, has a very nice property. Here again, doubled its definition, and it can be easily checked that this function is non-negative. So that if you define the quantum scalar product with this measure inside, and this is why it's labeled by the letter mu. So if you define the scalar product, then it turns out the Hamiltonians I wrote down at the very beginning are formally self-adjoint with respect to this scalar product with this measure. So this is really the measure function that enters the integral representation. And to prove this, it's actually not so hard to prove that this Hamiltonian is self-adjoint. You just use the difference equations for the double sign functions I showed before. So again, let me return. This was the construction of the operator by Holmes and Ruijsenaars. And after they constructed the eigenfunctions, they conjectured a lot of properties of these eigenfunctions that are interesting from the quantum mechanical point of view. For example, as Sergei Dokhachov already mentioned, in the case of Slother chain, you need these functions to be orthogonal and complete. And you're also interested, these are functions of continuous spectra, and they give some scattering amplitudes. You're also interested in asymptotics, and they also conjecture some of the symmetries of these eigenfunctions. And now let me state one of the symmetries which we proved with Sergei Derkachov, and Sergei Horoshkin. So this was the symmetry that they conjectured and proved in the case of 2 and 3 particles, but at different methods. And in what follows, I will explain how it proved in the general case. So again, this is just the construction of the Thomas and Ruijsenaars, and the eigenfunction is this recursive chain of the lambda operators at the end acting just on the simple plane wave. And if we also define the so-called reflected coupling, so this is just kind of reflection of the coupling G star, then it turns out that this integral, which is a big multiple integral, has a peculiar symmetry when we interchange the x and lambda variables, and when we also reflect the coupling constant G to G star. So this is kind of self-duality that was mentioned previously. We call it bispectral symmetry for the reason I will explain now. So again, this is the symmetry, and a simple corollary of the symmetry is as follows. You recall, by construction, this is just like a function of the Hamiltonians, which are some operators acting on the coordinates. And just by this symmetry, we have the same type of operators with which we can act on this function and which act on the lambda variables, and which depend on the G star coupling constant, reflected coupling. And with these operators, we have the eigenvalues which depend on the coordinates. So this is symmetry gives us the same setting of bispectral problem, which I explained at the beginning. And this is how this bispectral problem is realized in the Ruijsenaars model.
So this shift of the coupling is essential. Yeah, you cannot solve it.
Yeah, but the original Ruijsenaars Hamiltonians which wrote, they are bispectral without the shifts.
Yeah, that's what I'm asking.
Yes, and these are not the original. These are just similarity transformation of the original ones, and the similarity transformation depends on the coupling constant, so it breaks this symmetry. And in the original Hamiltonians, you don't have this G star. In the classical case, you also don't have this G star.
Yeah.
So this is very nice, and actually, Ruijsenaars conjectured this bispectral problem very long ago, just by analogy with the classical case, which he solved completely. And he used then this bispectral conjecture to derive some of the properties of the eigenfunctions, and it eventually, they with this conjecture they were able to construct the eigenfunctions. But this is really a long story. I just meant to explain that this is quite interesting thing. So you may imagine a lot of the other properties of this eigenfunction, which can be which can have corollaries due to this symmetry. So one simple property is that, again, this is just the integral representation written a bit more explicitly. And in this integral representation, as I said at the beginning, the coordinates are included symmetrically. So we have a bosonic particles. And this theorem, this is a simple symmetry. And this theorem tells us that as a corollary, the eigenfunctions are also symmetric with respect to the lambda variables, which is by no means obvious from this original integral representation. So it is really hard to prove actually that this integral representation is symmetric with respect to the lambda variables. And this theorem gives us this for free. And all of the other properties can be also doubled. So it saves you a lot of work actually. So asymptotics or integrals that can be calculated with this eigenfunction also can be can have this type of corollaries. Now let me explain how we prove this theorem. And first of all, let me explain roughly the main idea. So the main idea is very simple. This theorem, this formula, can be interpreted just as the equivalence of two integrals. The first integral from the left is just the integral which was written before. It's Helmholtz and Ruijsenaars integral representation. And the second integral is the integral which corresponds to this right-hand side, and which is the same type of integral, but it is recursive with respect to not the coordinates, but the spectral variable, gamma here. And it has some different, slightly different kernel here. It's just because we reflect coupling constants. So it has a difference, the difference is not so complicated, but these are still two different integrals, multiple integrals. And the way to prove that these integrals are actually equal is to show that both of these integrals are actually the reductions of one bigger integral, which is written schematically here. So this is kind of a standard trick. And now the main thing is that the main idea is that you can transform the kernel of the bigger integral, which I will show you at the end, probably. So you can transform it in two ways. And the first way will give you the integral, smaller integral from the right, and the second way will give you the integral from the left, so vice versa.
I ask the question. Because of this exchange of J, is it possible to make from like a G not equal to 0, G which is equal to 0, for example?
No, G should be positive, actually.
What?
G should be positive. It's one of the conditions.
Oh, okay, so omegas are positive, yes?
Omegas also positive.
Oh,
okay. Omegas and G are positive. It's
for the focus.
You can yes, it's this part.
So real parts positive.
Yeah, the real parts positive, and this actually in this talk I won't explain any details. So this is just analysis. Yes, Ruijsenaars consider the quantum mechanical problem. So you have this scalar product, and you have the self-adjointness only for the case of real parameters, and the complex parameters is just like the already not some quantum mechanical problem, but it's also interesting. But I will consider here in this talk only the real constants. So let me explain how this scheme can be realized. And here I wrote it just to return to it at the end. And in order to do this, we introduce in this model the new object, which is called, again, as in the previous talk, the Baxter Q operators. And this is a simple thing. If you already understood what are the lambda operators, the Q operators in this case differ from the lambda operators just by the following thing. The lambda operators increases the number of coordinates. So it acts on the n-1 functions of n-1 coordinates and gives n coordinates function. And the Q operator has the same type of kernel, but with the same number of integration variables and the coordinates. So all of the functions are the same. And this number n, which differs from this number n-1, is the only difference. So let me now, I will explain the motivation for this Q operators, one more motivation, because it just can be scary from the first glance. And let me before state two key properties of these operators. So first of all, these Q operators commute with the Hamiltonians I wrote down at the very beginning. So this is due to some remarkable properties of the kernels of these operators, and it is not hard to check actually this first property, but I won't explain it. So the Hamiltonians are known, the Q operators have some known functions in it, and you can try to check this first property just acting with the Hamiltonians on these operators. And the more complicated thing is the second property, which is expected from the first one. So since the Q operators and Hamiltonians commute, we expect that they will have common eigenfunctions. And it is indeed the case. The Q operators are diagonalized by the same eigenfunctions of the Hamiltonians in this way. And there are two remarkable features of the eigenvalues of these Q operators. So that's why we need them. The first remarkable feature is that these eigenvalues are factorized. So in each term in this product, we have only one spectral variable lambda j, which is the spectral variable of the eigenfunction. And the second thing, which is even more remarkable, is that these eigenvalues are written in terms of the same k functions as before. So here I again remind you that the q and lambda operators are built from the k functions, which were dependent on the coordinate and on the coupling constant g. This is the precise form of them.
So these key functions, they replace demo functions because
yes.
of the keys.
Yeah, yeah.
And for the first line, in Toda, like Sergio just explained, because in Toda it was possible to consider commutative to the generation function, which is related to these types of matrices. But here you have to check with each Hamiltonian independent.
Yeah, it's a universal check because you have a universal formula for the Hamiltonians, so it's actually maybe simpler in some sense. So I see. There are some known identities.
Do these Q operators commute
Yes, I will explain. Yes, they are commute between themselves. So the Q operators with different spectral variables commute. And I will. And it's homework for everyone, so to show that they commute. But I will return to this property later. So now, as I said, these K functions again are the same building blocks, but here you can notice that the coupling constant is already G star, reflected coupling. And this is already a glimpse of the symmetry, which I wanted to explain. So here, K functions depend on the spectral variables, not coordinates, and on the reflected coupling G star. This is why this property is important, and this is why we use it in order to do these transformations. So I will explain it. So let me now mention the motivation for these Q operators, which is quite heuristic and formal, but still. If you consider the Hamiltonian, which is one of the Hamiltonians I wrote down at the beginning, this is one of the simplest one. This contains just one shift operator, and it's labeled H1. And I also put it n in brackets just to emphasize that this Hamiltonian is for the n particles. So these Hamiltonians can have a very natural physical property that if you separate the particles, then the interaction falls off. And this means that if you in particular separate only one particle, xn, and formally send it to infinity from the rest ones, then the Hamiltonian, you can check it, just simple check, this Hamiltonian will separate formally into two operators. The Hamiltonian for the not separated n-1 particles and the shift operator for the n-separated particle. And also there is some constant, which is not important. So by this formal asymptotics of the Hamiltonians, we can expect that the same asymptotics will be present for the eigenfunctions. So we expect that in this limit, the eigenfunctions will also separate into two parts. The one is corresponds to the separated particle xn, and here we have xn coordinate, and the rest one is the eigenfunctions for the n-1 particle system. So, and also we expect that, of course, we don't specify the normalization of these eigenfunctions, so there will be some coefficient c, which will depend on the spectral variables, and it depends on the normalization of eigenfunctions. So we can just heuristically expect this from the property of the Hamiltonians. And actually, all of the other Hamiltonians also have this property. I just didn't try it here. And now let me consider the Ruijsenaars representation again and consider the same type of limit in it. So if you just took the explicit form of this lambda operator in this representation, then what you obtain in this limit is precisely the Q operator I defined previously. This is marked with red here. And so we expect that these two formulas will coincide, and this formula is more complicated because you have some integral operator which acts on the function. And therefore, we expect that this integral operator should be diagonalized by these eigenfunctions. And its eigenvalue will be given by this coefficient, which is undefined c, but should be some function of lambda. So this is the expectation, and it's not the strict art, proof, but now let me explain how this actually can be proven in the same spirit as
one of these formulas you see is very only asymptotically, while the other one is zero, yeah?
This formula is asymptotic expectation, and this formula is also asymptotics. So this formula is exact, and the second line is asymptotics of this exact formula.
So exactly to lambda and
yes. So the Q operator is the operator that appears in the limit from the lambda operator. This is one of its motivation to consider such operator once you have lambda operator. So now let me explain what is the path to the proof of this expectation. So as there was an answer about this, it turns out that these Q operators, it can be proven, commute with each other. This is one local relation for this type of operators. And this is a whole other story. So this local relation is some integral identity, which should be proved separately, but it's very technical, and I won't say anything about it. The part I need is that just as the Q operator appearing is the limit of the lambda operator in the same way, because they're very similar things, you can take a limit of the Q operator and obtain the lambda operator. So you can take then, if you know the first relation, you can take some limit, particular limit of it, and obtain the second relation, which contains already Q and lambda operators in it. And this is the relation that we will need for the diagonalization of the Q operator. So it's some useful local relation, which was also for the body chain, but there was not this K function, but the gamma function.
So this Q and lambda is the generating series of Q operators.
No, it's the Q operator itself. So the Q operator is actually not the operator, but the commutative family of operators, strictly speaking. So
previously you have given family of Q.
Yes, lambda is.
And lastly, this the generating series
of something.
Of Q operators.
No, we have name.
So what is the relation between Q and lambda and Q and K?
Q and K. So the Q operator is just the integral operator, which is.
I didn't have so the previous there are certain page there's commutation between Q operator and H operator.
Yes.
Yes. Okay. Only one operator.
Yeah. HS. Yeah, you could extract.
I thought you also have a sequence of Q operators.
No, it's just the Hamiltonians and the Q operators, and it turns out the Q operators also commute between themselves. You could exact the Hamiltonian from the Q operator, but it's really a long story. So now, as I say, this is the relation that you need for the diagonalization of this Q operator, and probably you already get the idea. But let me explain the reason why we have actually this K function that will be the function that will be included in the eigenvalue of the Q operator. So the reason is this integral identity, as it's simply as it is. So this integral identity tells us that the K function, which was the main building block of the Q operator and lambda operator here, its Fourier transform is given by the same function.
It's not Gaussian. Yeah.
It's not Gaussian integral.
No, I mean Gaussian.
Yeah, Gaussian and Hermite polynomials are also satisfy this property, but there are a lot of functions that probably that satisfy this property. But here we have a more peculiar thing because we also have a reflection in the coupling constant G and G star. So this is the reason why in here we also have the G star and why we have the G star in the symmetry of the eigenfunctions. So this integral is some special case of the more general identity, which was discovered independently in different contexts by Bosonic and by different Kashev and Volkov. But so here we just use the result in this deriving this limit from the first relation to the second. So in this limit, one integral separates, and this integral will be just this Fourier transform, and therefore we will have the K function from the right. For the Todd chain, you can do all of the same things. Okay. So if this is clear, then let me explain the main idea of the Q operator diagonalization. Probably it will be tautological to what Sergei Eduardovich said. So the main thing is that we have the recursive construction of our eigenfunctions. Very simple. We just have a chain of lambda operators. And we also have a local relation for the Q and lambda operators. So when you act with the Q operator, which is marked with red here, and it meets some lambda operator, then it exchanges with it. So they exchange their order and give you one coefficient, this K function. And then you will be in the same situation, but with n-1 particle system. So I guess the idea is clear. So you just apply this local relation at each step, and at each step you will have some coefficient K that will the eigenvalue of the Q operator will in the final result be the product of these coefficients. So again, I wrote down this the final result here. So the Q operator acting on the eigenfunction will be this product of the K functions that appear at each step. And let me now return. So this was the main thing that should be proven in order to prove this theorem. And once more, we have the appearance of this bispectrality property for this model, analogously to the case of Hamiltonians. If we believe that this theorem is true, or if we prove it, then we can write down the same kind of bispectral problem, but for the case of Q operators. So we already proven the first line. We have a Q operator, which is the integral operator acting on the coordinates. And therefore, this symmetry tells us that we have the same type of operator, Q hat, that acts on the lambda variables and which contains the same K functions with the G star coupling. And then in turn, its eigenvalue will be given by the K functions that will depend on the coordinates and the usual G coupling, just because 2 times reflection is identical operator. So G star star will be G again. So this is one of the corollaries, but this corollary can be used to prove this theorem by induction. So in the simplest case, let me return to this. In the simplest case, when you have only one particle, the symmetry is trivial. So you don't have any coupling constant, and you have only this lambda and x variables, which can be interchanged freely. And then we can assume that in general, we have proved that this theorem is true for the n-1 particle case. And therefore, we will have, as a corollary of this assumption, the bispectral problem for the Q operators. We will have the diagonalization of the Q and Q hat operator. Now, this is from the assumption. And now I wanted to explain how this general scheme, general idea, with some bigger integral here applies. So we have some, at the beginning, we have some integral representation, and we are playing from it a bigger integral representation, which includes now both Q and Q hat operators. So this is some bigger integral, because in Halmos and Ruijsenaars representation, you have only one operator, lambda. And here you have Q and Q hat operator, which both are integral operators. And this integral is precisely in this scheme, this bigger integral, which is which dimension is 2 times n-1. So to recover the original representation, you just act with the Q hat operator on the eigenfunction, and you will obtain this K function. And after some work, you will realize that this is the original eigenfunction representation of the Halmos and Ruijsenaars. So we want to prove this thing for the general case using this bigger integral representation. And the proof consists of just commuting these Q and Q hat operators.
Sorry. So in this Halmos representation, it was also a curse, yeah?
Yes.
This one. And so what was there as an operator?
Yes.
Just a reason, because this you say has one extra integration.
Yes.
Yeah.
To recover their thing, you should act.
There was some down there. Yeah?
Yes. There was lambda, and actually, you have a very simple relation that if you just look at the kernel of the lambda operator, then the lambda operator after some unimportant exponent is just the Q operator on the n-1 case times the product of the K functions that are written here, the same type of K functions. I'm not sure if it's visible, but still. So this is the product of K functions. So this is just simple consequence of the definition of the separators, and here we use it to recover the original integral representation. So again, the main idea is to prove this formula, and we prove it just by rearranging the separators. So now, if we took the Q hat operator to the beginning and Q operator with actually the Q operator on this eigenfunction, then we will use again this bispectral problem, and we'll have some the right hand side of this bispectral symmetry. So this is the path from here to here to this to the second integral. So the equivalence of the integral representations, the symmetry, is just the commutation of the Q and Q hat operators. How much time? 15 minutes. 15 minutes, okay.
But do they obviously commute?
No, it's not obvious. Algebraically, it's obvious because the Q operator acts on the coordinates, Q hat operator acts on the lambda variables. And actually, when you do any local relation, the local relation I showed you before, this kind of thing, you do it inside some big multiple integrals, and you should justify that this integral are absolutely convergent. And there are some non-trivial bounds should be used. So I won't discuss it here, but it can be done also. So Ruijsenaars also derives some non-trivial bound that will be applied here just to justify that this integral representation has a meaning. So it's absolutely convergent integral. We should prove it. Now, this is the main idea. Probably it's all I wanted to say. Let me return for a minute. So this is the bispectral symmetry. As I said, this is proved using this bispectral problem for the Q operators. And the same kind of construction can be done for the total chain, which was described by Nikita Belousov. So he didn't mention this Q hat operator actually, I suppose, but the same kind of things can be done. And were partially done. So this is one of the remarks. Similar constructions can be done, can be made, and were partially made in the other relative systems. As I say, this Ruijsenaars system can be reduced to the collinear system by some limit. And the open to the chain is relativistic or non-relativistic is also a limit of this Ruijsenaars model. So the Ruijsenaars model is like the biggest thing in this family to my knowledge. And also the spin chains, which are kind of different, but
to get open total, you can get it from the logical settlement,
yes,
but limit is very not real.
Yes, yes. I don't know how you should do this. The idea is clear because you have the exponential tails.
Stuff, but I don't know how to do it.
Yeah, it's
carefully in your context.
It's a different problem, so you should start with these formulas or forms of similar formulas for the Collier-Sutton, and it's a difficult problem to take all of these limits actually. So there's also some convergence arguments that should be made. It's very difficult, but we aim to prove we didn't write the paper now, but we aim to write the paper for the limit of the Collier-Sutton, which is kind of simple. So the other conjecture, eigenfunctions properties. So as I said, they had a list, the Helms and Ruijsenaars had a list of 5 or 6 properties of the eigenfunctions. One of them was bispectral symmetry. The other was, of course, the orthogonality and completeness. There was also some other symmetry and asymptotic symmetry, and also some other property. So all of them, most of them are now can be proven. And in the case of bispectral symmetry, orthogonality and completeness, and some other coupling constant symmetry, you can use, to prove these symmetries, you can use Q operators. And the idea is very simple, the same as the chain. This was done in our joint work with Sergei's. So finally, let me mention some sources of inspiration. I think I won't read through it, you just read the names by yourself. So a similar bispectrality proof was done actually for the open Toda chain, and we were inspired by the details are different because in Toda chain you have boosters and integrals, local relations, and here you don't have it. So it was more difficult probably, but it's still, now we see that the scheme is universal. And for your question, actually, yes, the Q operator which we introduced, the kernel of this operator also gives the Beckman transformation of the classical collision. This Beckman transformation was investigated by Helms and Ruijsenaars in the paper. So I think this is all I wanted to say. So thank you very much for your attention.
But it's local properties, so you don't have this local relation, which is described by differential feeling diagrams.
Yes, if you try to write the Feynman diagrams in the Toda chain, that you will obtain something like Sergei was dictating, so you will obtain something like this. When you have, for example, the conductivity of the Q operators, these are integrals. And probably you can just add any other legs, any number of legs here. But in the case of the Collier or the Ruijsenaars system, you have a very complicated graph. So you have a full graph between all of the, for example, in the case of free particles, you have some kind of this. This is obviously not local. You have some kind of integrals like this, which you can try to predict that. And we don't see any local relation.
And so this multiple lines, it's so that's
okay.
Affected all particles interact with each other. Yeah,
seems like that, but we don't know like the actual root. If you have the potential which is non-local, you will have the typical rotation that is non-local. But observation is like that. Yes, experimental observation. In all of the models where you have such non-local potential, you will have the simple representation that will be non-local. And in the spin chains and Toda chains, which are near the nearest neighbors, models, you have such local representation.
If you start with G equals omega 1 plus omega 2, this
it is actually another. G should be more than 0 and less than 1 plus omega 2. It's enough because the Hamiltonians actually are periodic with respect to the G, so you can just put G plus omega 2, and then you will obtain the same kind of potential. So it's enough to consider G in some quantum interval, and this interval you consider is enough. But you can't just, I'm not sure. Probably the integrals will be some explicit calculated integrals in this case, but I'm not sure how you calculate.
So this not give you something, not trivial, yes. I mean, because if there was no such condition yet, you could obtain from some trivial system a trivial one. Because
yeah, I think
it's related to
Ruijsenaars and Yeah, I don't know about this kind of specification, G equals to omega 1 plus omega 2, but Ruijsenaars it has in their paper considered when G equals to omega 2 is trivial because it will be just the period, and G equals to omega 1 in this case is not trivial. But the double sign function is symmetric with respect to omega 1 and omega 2, and actually this integral representation can be explicitly calculated in the case G equals to omega 1. And this is what I think you're asking. So you obtain non-trivial Hamiltonians, but the eigenfunctions are actually some simple formula in this case, but it's not the case you're asking. G equals omega 1.
Could you comment on the role of the building block of your instruction, quantum derivative function, in the spectral duality? So how the role of this function essentially plays the same role, it should be changed by some other function, or it represents the symmetries of these functions.
The role is as follows, I think. So we don't use the quantum logarithm, we use double sign, but the quantum logarithm can be written as the double sign plus some simple exponent. And actually, these KMU functions are even not the double signs, they are ratios. So they are even more, they have different properties, but one of the properties is that both the logarithm and double sign functions are symmetric with respect to the omega 1 and omega 2 parameters, and therefore you can have not only these Hamiltonians I wrote, but the Hamiltonians with permuted omega 1 and omega 2. So the symmetry of the building block tells you that actually your eigenfunctions are eigenfunctions of one more collection of Hamiltonians, which are the Hamiltonians with permuted omega 1.
But it's not the symmetry between coordinates and...
Yes, the symmetry is due to this integral identity, which is not for the quantum logarithm itself, but for some product of the logarithms. So this is the identity which was written in terms of logarithm in this paper setting. And this identity can be decoded. This is just two logarithms. Two logarithms here, and actually three logarithms here. But
it's suppose that this property is equivalent on some property of the diagonal.
Yeah, it is indeed true. And if you look at these papers, you will find that this integral is
just the pentagon equation for derivative.
I don't think that this pentagon is simpler, I think. Yes, simpler, yeah. Pentagon has three logarithms in the integral, I think, yes. And here we have two logarithms here. So it's simpler, but still. It's this integral actually is a generalization in the same sense that the double sign function is a generalization or deformation of the gamma function. This integral in the limit, classical limit, it turns into the beta integral when you have usual gamma functions here and you have here some rational function. So this is what's kind of integral. Beta integral.
Okay, let us end the speaker again.